We will now discuss a very important result. This is called Poincare's inequality. This will play a very key role in the study of Dirichlet boundary value problems for elliptic equations, which we will on other PDEs as we will see later on. Okay, to start with, up to now we've been looking at extension theorems, and we saw fairly elaborate conditions which are needed on the boundary or the domain so that there exists an extension operator. One can always ask, why can't we just simply extend by 0? So u is a function from omega to r, and then I have u tilde extension by 0. So u in w1p omega, does it imply that u tilde is in w1p omega? This would be the simplest Rn, sorry. Answer is no. For instance, if you took the function, take the interval 0, 1 in R, and you take the function u identically equal to 1, and then you show, so u will belong to w1p of omega for any 1 less than equal to p less than equal to infinity. U tilde is not in w1p of Rn. So I will leave you, so exercise. You will check why. So you should be able to see this very easily. Okay, so extension by 0 is in general not allowed. However, if we work with w1p0 of omega, then it happens that extension by 0 is always there, and this is independent of the domain. So however bad or good your domain is, it doesn't matter. Extension by 0 of a w1p0 function is always in w1p of Rn. So this is the nice property. So we have the following theorem. Let 1 less than equal to p less than infinity, let u tilde denote the extension by 0, 0 outside omega of u from omega to r. Then if u belongs to w1p0 of omega, we have u tilde belongs to w1p of Rn, and for all 1 less than equal to I less than equal to n, you have the du tilde by dxi is nothing but du by dxi. Tilde. So omega is open subset of R. So omega open subset of Rn. Okay. So let us prove. This is very simple proof. So u in LP of Rn always implies that u tilde is in LP of Rn, even the norm doesn't change, okay, because you have added nothing but 0 outside. So if du tilde by dxi is du by dxi tilde, then that will also show that u tilde is in w1p of Rn. So enough to show star. So star is this relationship here. So we just have to show the derivatives. So u is in w1p 0 of omega. So that means there exists un in d omega such that un converges to u in w1p omega. So this is the definition, because w1p0 is the closure of d omega with respect to that norm. Okay, let phi belong to d of Rn. So you have that integral on omega un d phi by dxi dx is equal to minus integral dun by dxi phi. This is just a distribution derivative definition, and anyway they are all smooth functions. There is no boundary cut. Sorry, this is not distribution derivative. This is phi is in d of Rn, remember. Un and phi are all smooth functions. So I am just doing integration by parts. So you have minus integral on omega dun by dxi phi and no boundary term, since un is in d omega. So sorry, d of omega. So it vanishes on the boundary, and therefore you will never have any boundary terms. So now you just simply pass to the limit. Because now phi is a smooth function, it's in all the LP spaces. It's a d of Rn function restricted to omega, so it's in all the LP spaces, and therefore un and dun by dxi converge in LP, and therefore you have, so passing to the limit, you have integral on omega u d phi by dxi dx is equal to minus integral on omega du by dxi phi dx. And now this is same, this is, that is integral on Rn of u tilde d phi by dxi dx is equal to minus integral on Rn du by dxi tilde phi dx. This proves star, and therefore the theorem is proved. So if you are in W1P0, we are in a very happy situation. You just have to extend by 0 to get it. So now we have the important theorem. This is called Poincare's inequality. So let omega contained in Rn be a bounded open set. So this is an important hypothesis, bounded open set. Let 1 less than or equal to p less than infinity, then there exists a constant c which depends only on p and the domain omega, which is strictly positive, such that mod u 0p omega is less than c times mod u 1p omega for all u in W1p0 omega. In particular, u going to mod u 1p omega defines a norm on W1p0 omega equivalent to norm 1p omega, the bigger one. Okay. If p equals 2, h10 of omega is a Hilbert space for the inner product uv1 omega equals integral omega sigma I equals 1 to n du by dxi dv by dxi dx, which is equal to integral omega grad u dot grad v dx in the standard notation, yielding the norm mod 1 omega, which is equivalent to the norm norm 1 omega. Okay. So, this is the theorem. So, what is this saying? So, normally mod u 1 p omega is only a semi-norm. This is what we were saying. Why is it a semi-norm? Because if mod u 1 p of omega, that means du by dxi are all 0, then that only says u is a constant. It does not imply that u equal to 0. Now, if you knew that u vanishes somewhere, then of course it is a constant vanishing somewhere, it has to be identically 0. And I have been hinting throughout that w1p0 of omega are in fact functions which in some sense vanish on the boundary. Therefore, if it is a constant vanishing on the boundary, it better be 0. So, this is the idea. We haven't proved that, of course. So, but we can prove that, we can prove this result, that in fact it is a norm in because u equals 0. Why is it equivalent? Of course, you have that mod u 1 p omega is of course less than or equal to norm u 1 p omega. But now we are saying that mod u, but what is norm u 1 p of omega? This is mod u 0 p omega power p plus mod u 1 p omega power p whole power 1 by p. Okay, and if mod u can be expressed in the Poincare inequality test, this can be estimated in terms of this other one, and therefore the whole thing becomes less than some c times mod u 1 p omega, and therefore you have equivalent norms. The case p equals 2 is obvious, so we have that this is true. Okay, so now let us prove this inequality. So this is called Poincare's inequality. So proof. Let omega be a box, so minus a whole power n, a positive. Let u belong to d of omega, 1 less than p less than infinity. Let us assume the case 1 less 1 equal to p is even easier. You will see it in a moment. Why? Okay. So now by the fundamental theorem of calculus, ux can be written as integral minus a to xn of du by dxn x dash t dt. Okay, this is just a fundamental calculus. So recall our notation: x equals x dash xn, x dash equals x1 up to xn minus 1, the first n minus 1 coordinates. Okay, so by Hölder's inequality, mod ux is therefore less than or equal to integral minus a to xn mod du by dxn x dash t power p dt whole power 1 by p, and then you have here the function 1 is the other function. So when I integrate it, I will get mod xn plus a power 1 by p dash. Okay, so that is just the this thing. So if p equals 1, I will just simply say this is less than or equal to integral. You don't have to put anything else after that. You just get mod this. That's all. Okay, so you mod ux is less than or equal to integral mod u du by dxn. That's all. That's the standard. So p equals 1 is easy to cover. Everything else will now follow from the. So 1 by p plus 1 by p dash. This is the conjugate exponent equal to 1. Okay. So mod ux power p, I am going to take the pth power, that's less than or equal to integral minus a to xn mod du by dxn x dash t power p dt into mod xn plus a. I will just write it as 2a less than or equal to 2a, because mod xn is mod xn less than a, and therefore and then I get p by p dash. So now integrate with respect to x dash. Okay, so mod ux dash xn power p integral dx dash, okay, is less than or equal to 2a power p by p dash, okay, and then integral with respect, already you have integration with respect to dt, and now I have to integrate with respect to dx dash, so, and that will give me exactly integration with respect to omega mod du by dxn power p dx. Now you integrate with respect to xn. Then I will get integral on omega mod u power p dx less than or equal to, now this is a constant, integral on omega mod du by dxn power p dx, that is a constant, 2a power p by p plus 1, and then I am integrating the function, constant function from one constant function 1 from a minus a to a, so that will pick up one more 2a, so into 2a into p by p dash plus 1. So now you take the pth root on both sides, you get mod u 0p omega less than or equal to 2a power 1 by p dash plus 1 by p, that is 1, and integral mod u 1p omega. In fact, it is only the derivative LP norm of du by dxn that is less than the sum of all the first derivatives, and therefore you have less than or equal to mod u 1p of omega. So this is true for all u in d omega. So if u belongs to w1p0 omega, you have un goes to u in w1p omega and un in d omega. So this inequality is true for un, so mod un 0p omega is less than or equal to 2a times mod un 1p omega, and now you pass to the limits, and that will imply that mod u 0p omega is less than or equal to 2a times mod u 1p omega. So this proves the theorem when omega is a box. So if omega is a bounded open set, so we are using that hypothesis now, then there exists a positive such that omega is contained in omega tilde, which is minus a power n. You can put it in a sufficiently big box, and then you take u in w1p 0 of omega, and this implies that u tilde belongs to w1p 0 of omega tilde. By the previous theorem, extension by 0 gives you in fact w1p Rn function, and then u can be approximated by un in d omega, which is also in d of omega tilde, and in LP norm, and u tilde nothing happens outside omega, so everything will be okay. So you can check this. Okay, so this implies that mod u tilde 0p omega tilde is less than or equal to 2a times mod u tilde 1p omega tilde, and that is because nothing happens outside omega, mod u 0p omega is less than or equal to 2a times mod u 1p omega. So this completes the proof of Poincare's inequality. So we make a few nice remarks. One, if omega is bounded in one direction, that is, say, omega contained in a strip of finite width. So you have some two parallel lines, and then omega is somewhere in between. It may be an unbounded domain, it need not be bounded. Now since our proof integrated only in one direction, namely the xn, so you can do the same thing in this direction, and therefore above proof works. And Poincare inequality true. However, it does not work for truly unbounded domains. For instance, if you took zeta in D of Rn, which we have seen many times before, so such that support of zeta is contained in B 0, 2, and then zeta identically 1 on B 0, 1, ball center origin radius 1, 0 less than or equal to zeta less than or equal to 1, and you take zeta k of x is zeta of x by k. Then we can show if p is bigger than n, that mod zeta k 1p Rn goes to 0 as k tends to infinity, but mod zeta k 0p Rn, recall it is 1 on the ball cent, so it is bigger than or equal to the Lebesgue measure of the unit ball. Of the ball k, sorry, because it is 1 on the ball of radius k, so this is b0 k power 1 by p, and this of course goes to plus infinity. So you can never have a Poincare type inequality. So mod zeta k 0p omega less than Rn mod c times mod zeta k 1p Rn, not possible. So you cannot have Poincare's inequality in truly unbounded domains. The other thing is, if omega is bounded, then u identically 1 is in W1p omega. But mod u 0p omega is not 0 and mod u 1p omega equal to 0. Therefore, u does not belong to W1p0 of omega. So, we have answered a question which I raised long ago. So, you have the W1p0 of omega is strictly a subset of W1p of omega. Recall in Rn we showed that both these spaces were the same, but if you have a bounded domain or even a domain which is bounded in one direction where Poincare's inequality is true, you can show that if Poincare inequality is true, then this is always a different subspace. Okay, so this is the thing. 3. Next remark, let us take u in W2p0 omega. So this automatically implies that u is in W1p0 of omega, because du of a sequence from d omega approximates the first derivatives, second derivatives and the function, and also du by dxi belongs to W1p0 of omega, because again the same sequence, if you take the derivative sequence, that will approximate this in LP and all its first derivatives in LP as well, and therefore this is true for one less eigenvalence here. So by Poincare's inequality you have du, so omega bounded, dxi 0p omega is less than or equal to mod du by dx c times dxi mod 1p omega. That is mod du by mod u 1p omega is less than some c times mod u 2p omega. And again by Poincare's inequality we have that mod u 0p omega is less than or equal to c times mod u 1p omega, which is now less than some c dash times mod u 2p omega. More generally, if m is any integer greater than or equal to 1, u in w mp0 of omega, you have mod u 0 p omega is less than or equal to c times mod u mp omega, and u going to mod u 1 mp omega is a norm on wmp0 equivalent to the norm mp omega, because all in between derivatives can also be bounded by mod u mp of omega. So this is the thing. Now the constant which we got, this constant c, is something like the diameter of omega, because if you took a box, then you saw that 2a was the constant, and if you otherwise you put it inside a box, if the smallest possible box will again have 2a as like the diameter of omega. So something like diameter of omega will be the constant, but that's not the best constant. The best constant has a very interesting connection to what are called eigenvalue problems, and we will see that later.